So we learned a little bit about derivatives on their last set of videos, and now we want to talk, and then one of the last things we covered was antiderivatives. And that leads us to this idea of the integral. And so with this set of videos, we're going to talk about the engineering applications of the integral. And one of the first ones we want to talk about is area under a curve. So with area under the curve, we can take a function, and for this example, we're going to use this function. So we have f of x is negative 0.8x plus 20. So the first thing I need to do is to draw that out. And so the nice thing about this is having graph paper, whereas previous time, or having engineering paper, that where previous times I've just drawn quick sketches that weren't necessarily to scale. This time we're going to draw everything out a little more precisely. I've measured and made each block a square. And so when I draw the curve, I know it starts at x is 0, f of x is 20 because the intercept is 20, and it has a slope of negative 0.8. So I can do it at different points along the way. At 10, I would get 12. At 20, I would get 16, and we know it crosses here when x is 25. And so I've tried to draw that fairly accurately. And then what I want to know is, what is the area under the curve between x is 5 and x is 15. So what we're talking about is this area right here. So this is the area I'm trying to find, is of this trapezoid looking shape. And the first way we want to do that is just by counting the squares. Like I said, I've got to draw a nice into scale on engineering paper. I can just count up how many squares in there, and I can just see how many there are. So if we start doing that, kind of give you a count row by row, or column by column really. One thing I know that will help is if I kind of draw it up here. I've got this square here that is where at 15 the value is 8. The value of the function is 8. So I know from 8 down is in all of it. So I've got an area that's 8 high by 10 wide. So the area of this part is 8 by 10, which is 80. So I can just count those squares quickly, and then start counting how many extra are on each column. One of the things I run into immediately if I start counting these, 1, 2, 3, 4, 5, 6, 7, is that I have a little bit left over. So I'm just going to call that 7 plus. I only want to count full squares. But if I go to the next row, 1, 2, 3, 4, 5, 6, and that's 7 plus a little bit more. So let's say I count that as 6 plus. Maybe I combine that and count a whole one there. So how accurate I want to be there, I only want to try to count full squares though. I'm not going to try to guess at decimal points at this point. So I'll just kind of say, yeah, that's a little more than 1, that's a little more than 1 combined. It looks like that's more than 1 full square between those two parts. And we'll do that kind of the rest of the way down. So if I count them up, I get 7 and 6 and 5 and 5 and 4 and 3 and 2 and 2 and 1. With these little bitty parts, I kind of add together. Like I said, we picked up 1 there, 1 there, 1 there, maybe 1 there. And so if I add all those in there, so I get 80 plus all of this, 7 and 6, 13, 18, 23, 27, 30, 32, 34, 35, 36, 37, 38, 39. So I would say that's 119 is the area. And this doesn't really have units, it's just however many squares. Maybe we're saying they're all 1 inch, whatever the case may be. So it might be 119 square inches, but mainly it's just 119 whatever the units are. But just counting up the squares is not necessarily a real scientific method of doing things. So maybe that's not, the best way we want to do that. One thing we can do in this case, we can calculate a more accurate result because this is a nice little shape, as we said before. It looks like a trapezoid. So part B wants us to actually calculate more accurately what is the area under that curve. So if we look at it as a trapezoid and kind of turn it on its side, we know we kind of take this and we've essentially tilted it that way. Yeah, we know that this distance here is 10. We know that this shorter length is 8, because at 15 it goes to 8. And down here, this longer length at 5, it goes to 16. So that's 0 to 16. So we know this is a 16 by 10 by 8 trapezoid. We don't have to know the diagonal there, although we could find it using some splitting it up into a triangle and using Pythagorean theorem. But then we just have to know area of a trapezoid, so hopefully we remember that from elementary school. That the area is 1/2 base 1 plus base 2 divided by the height. So in other words, we add the bases together, take the average of these being our bases, multiply by that height, and that will give us the area. So for our particular case, that's 1/2. Base 1 is 16. Base 2, which is the top, is 8. We have a height of 10. We can multiply that together in our calculator, or maybe do it by hand. That's 24 divided by 2 is 12. Times 10 is 120. So we're pretty close. So that would be the actual area of it. We counted up and got 119. So we were pretty close. So our counting squares method works pretty well, at least with a trapezoid, where we can get it. So what happens if we get a more complex function? So here we have a more generic curve. It's just a random kind of wavy thing I drew. We still label our axes f of x and x. And we want to know what is the area under the curve between A and B here. So to do that, we use kind of the same idea. So in 1869, a German mathematician named Bernhard Riemann said, well, if I have this, I can just cut it up into squares, take whatever my values are here, break it up into equal pieces, so for instance there I've got 4 equal pieces, and make each part a representative rectangle. And then just calculate the area of those rectangles and add those up. Okay, so I start drawing these rectangles in here. And you can see already there's a little bit of a problem. So I decided to divide it up into 4 rectangles. Why 4? Because that's what fit easily on here. And so I chose that. But then I have to figure out what height I'm going to choose for my rectangles. And so already I can see I do need to make sure that they're equal rectangles. So each one of these has a width of delta x, whatever that amount is. Like I said, since I use 4 rectangles, it's a fourth of whatever that distance is. But I also have to pick a height of that rectangle. If I choose here, I can draw the rectangle all the way up here. But then I've got this area that doesn't really belong in the curve. If I choose down here, then I lose all of that area. So the best kind of compromise is I'll just say I'll pick a point in the middle and draw it flat across from there. So we'll just pick the center point of each one of these. So again, so I would lose, so I'm counting some extra space here, I'm losing some extra space there. All that should kind of even out if I'm doing it on a normal curve. Yeah, and we see kind of got a little mix of all three different situations. On the second one, it looks like maybe I'm missing more area than I'm picking up. On the last one, I'm adding some extra areas and not losing very much. So, like I said, all that should balance out in general. So I'm going to call these f of x1, f of x2, f of x3, f of x4, because we'll just call each of these points, since I've used 4 divisions, I've got 4 spots I'm looking at. So then what is the area of my curve? So the area of my curve is, just these 4 rectangles, areas 1, 2, 3, and 4. And so if I get those individual areas, this is going to be delta x times f of x1 plus this one is delta x times f of x2, and so on. So one thing I can see pretty quickly is I can factor out delta x in all of those. But what is delta x? Well, delta x is equal to, what did I do? It's the 2 points that I have, b minus a, that total width, divided by, in this case, 4, or however many rectangles I have. Like I said, I use 4, so delta x on each one of those is a 4th. And so then my area is, if I use summation notation, I can rewrite telling it to add up these 4 things as the sum from I equals 1 to 4 f of x of I. So I can just generalize it that, however many I have, take all those, add it up. That's what the summation symbol means. So I'm going to take all those, add them up, multiply by delta x. And that's how I get my area. Where this is my width of each one, and this is my height of each one. Alright, and like I said, I don't know what the function is or what these values are, so I can't get an exact answer here. But that's the general idea behind doing this. And we call those Riemann sums. The Riemann sum says take it, cut it up into squares, take it, cut it up into squares, find the areas of those squares, and add them together, and that'll get you a good idea of the area under that curve. And so we have this concept of Riemann sums, where the area is our delta x times the sum from I equals 1 to n of f of x sub I. So, like I said, in our example, we had 4 points, so we had 4 values of f of x, and we added those 4 things together. More generically, we can say we have any n amounts of divisions, and you can get it that way. So, using that, we can have more and more rectangles. We could go to 6, we could go to 8, we could go to 100, right? So, we can see pretty quickly, we could go to 8, we'd cut it in half, and if we cut it, the more we cut it, the less we're off here when we make our estimate, right? If I were to cut this in half and do 1 from between there and there, now I get very little on each side that's different. And then I would have a point here in the middle where I would get a little on that side, miss a little on that side. I get a lot closer to getting the exact. I could get a lot closer to getting exact answers the more I get, right? So what happens if I make n bigger? Well, if I'm making n bigger, more divisions, well, if I cut If I have twice as many divisions, then delta x is only half as big, right? It gets smaller. So the more divisions I make, the smaller the more divisions I make, the smaller my widths are for each one. And as we just showed, the more accurate my heights get. So what happens? We just learned about limits a while back. What happens if delta x gets much smaller? In fact, since we just talked about limits, what happens if delta x goes to 0? Infinitely small. Or the word I like, infinitesimal. It's a good word. I always liked it, I don't know why. Yeah. Then what we have for area is this. And so I've taken our Riemann sum and I put the delta x back on the right hand side. But the limit as delta, I said delta goes to 0. This is actually should be delta x goes to 0. Limit as delta x goes to 0 of this, we're making it infinitely small. As I said, that should be what gives us the most accurate part, right? Because if we get so close that our width is infinitely small, then we don't have error hanging off of each side. Just like when we did slope with derivatives, when we made it an infinitely, when we chose points that were very far apart to get a slope. You know, we chose here and here, we got the slope that might be somewhat close. Here to here, we got better. As we got closer and closer, we got exactly what the slope was at that point. Same idea for area. Is, you know, if we have between here and here, we've got quite a bit of error. But between here and here, a little less error. Between here and here, and as we get closer and closer, we're right on that point and getting an exact amount. So that same idea for an area, what we call this is the integral. And so the area would actually be the integral a to b f of x, and our delta x becomes a dx. Again, very much runs parallel to what we talked about with derivatives. We had in derivatives, we had this idea of the slope was delta y over delta x. We did the limit as delta x approaches to 0. In other words, got closer and closer. And we came up and we were given the derivative. Same concept here, only backwards. Instead of doing slope, we're doing this idea of area. But as delta x goes to 0, we get an integral with the dx. And the way we would talk about this is we would say that this is the integral from a to b of f of x, what's in the middle, with respect to x, because it's dx here. Another way we talk about this is we take the integral from a to b. The value is capital F of b minus f of a, where this capital F of x is what we would call the antiderivative of f of x. In other words, it is the function that if we were to take the derivative of it, we would end up back at f at x. So that's why we call it the antiderivative. It's going the other way. And like I said, we got a little bit of glimpse of that from the last example of the derivatives homework where we did the sketching. We're given the acceleration and we work backwards to get velocity and work backwards from that to get position. What we were really doing with that was creating an antiderivative, the function that what the function would be that gives us that derivative. Okay, so big concept we just unleashed there. So how can we use that to solve our problem that we were dealing with earlier with our area under the curve? Okay, so if we revisit our previous question that f of x is negative 0.8 plus 20 and try to figure out the area under that curve using the integral, we know from what we just learned is that the area is the integral from 5 to 15, our points from a to b, of our function dx. The only question we have now is, how in the world do I get the antiderivative? of, of that. Again, it comes back to being able to use some handouts, you'll find that you should have this one available on Blackboard. Again, it kind of maps things out using antiderivatives. So given a function, what is the antiderivative? And one of the first key rules we find is, just like we found with derivatives and with many other things, the good news is if we have two functions added together, we can just do the parts individually. So what does that mean for us here? Well, let's look at that. So what that tells us is that we can take this and split it apart. So we can take this to be the integral of 5 to 15 of negative 0.8 of x times dx plus the integral from 0 to 5 to 15 of the 20 dx. So we just split it in half and can do each part by itself. All right, so then how do we evaluate those? We'll move it down here to another line. All right, so the next rule that's going to help us, is that, again, just like with derivatives, if we have a constant times that function, then that's the same as integrating the function with the constant out front. So let's apply that. So again, if we use the constant rule, that tells us that we can take this negative 0.8 and pull out front. We can pull the 20 out front and just think of this as a 1 integrated over here. Or technically in writing, we wouldn't even have to include that 1, but again, as we're getting comfortable with it, we can include that 1. So then we have to just integrate each part. So let's look at that. All right, so I'm trying to integrate this x dx. I know I've got a constant out front, and I'm only getting the antiderivative of that. We have a power rule that's similar to what we had well, it's going to be the exact opposite of what we had with derivatives, right? So when we took a derivative of a function, we brought down the power, we multiplied by the power and subtracted 1 from it. So to do the antiderivative, we do exactly the opposite. We add 1 to the power, and we divide by that new power that's had the 1 added to it. And you'll also see that all these have a plus c as a constant. And that's because whenever we do an antiderivative, because the derivative of a constant is 0, we could have had any constant added to this before we added things. So that antiderivative will have a plus c with it. So for x, what that tells us is we're going to take x. Right now it's to the 1 power, so we're going to make it squared, and then we have to divide by that new power. And we add c to it. And then to determine what it is on the interval from 5 to 15, we have to evaluate it at 5 and 15. And so we just kind of denote that on the end right there. Don't get confused in thinking that those are powers. Those are just showing that we're evaluating it from 5 to 15. Similarly, for the second half of this, we'll have the 20. When we integrate 1 with respect to dx, what we're going to get is a couple ways of thinking about that. One is, remember, whenever we have a constant here, that's like having a flat line. And so when we integrate it, we would end up with a line of that slope. So, or the other way of thinking about that is, if we remember back when we're doing derivatives, if we had an x to the 1, we took the derivative, we got x to the 0, which is 1. So this turns out to be x. So remember, 1 is the same thing as x to the 0. So I have to raise it to 1 and divide by the new power, which is 1. Or the more simple way to know that is just the integral is 20x. And again, I would have to add a constant on there. And I'm evaluating it from 5 to 15. Okay, so we're going to take this equation and drag it onto the next sheet because we obviously ran out of room there. And so again, we're still thinking about this idea of the antiderivative evaluated at a function. So again, notice on each of our things we have from a to b, which in our case is from 5 to 15. is we have to put those values into the function. So let's do that. So here what I've done is I've put in the upper term, the term on the right, put it into the function, subtract what I get when I put the lower term, the term on the left, into the function, and did that for each part. Then I could evaluate it or simplify it. And one thing I find in simplifying it is, although I included these constants on there because I was told I had to when doing an antiderivative, if I'm doing it and evaluating between the 2 points, I see that that constant gets added in one place, subtracted in the other place, added in one place, and subtracted in the other place. So I really could have ignored that. And so in the future, what we'll see oftentimes is when we're writing it, we'll just ignore, if we're evaluating it between 2 points, we ignore the plus c. Now, if we're just talking about what is the antiderivative of a function, we do have to add that on the end or we'll make it counted wrong. But if we're as we evaluate it between 2 points, they cancels out, so we can't ignore it. All right, so let's simplify it a little bit further. 225 over 2 minus 25 over 2, I get 200 over 2. 15 minus 5, I get 10. Multiply those things together. This is really just 100 inside here, so 100 times 0.8, I get negative 80. 20 times 10, I get 200. And wouldn't you know it, just as we found out, seems like an hour ago, in getting these, we find that the area under the curve that we had from a long time ago gets 120. Which, again, we know we got a much simpler way because we could use it as a trapezoid. We counted squares and we got close. But this is a completely precise answer. And the good news is we can use this with more complicated functions. We know we can do antiderivatives of things like sine and cosine and e and all these sorts of things. We have ways to get those. Whereas drawing them out and counting a cosine function, very annoying. Or, you won't get exactly a trapezoid if you have a function that has a sine or a cosine or an e in there. So, very precise way that we can apply this to much more complicated functions. The key parts we learned here kind of at the end is that for an integral, we can integrate it by taking the antiderivative at point B minus the antiderivative at point A. We learned that we can, in order to get that antiderivative, we can break things apart using the adding rule. We can pull things out front using the constant rule, and then we can use the power rule if it's a polynomial type function to get that. So those are things that we'll definitely use over and over, not only for this unit on integrals, but of course in your calculus class next semester.